So you guys ready to roll? All right. So what we're going to do is learn how to make one of these deformation mechanism maps, and then learn how to make these Christmas tree or pine tree or strength depth or parrot beak diagrams, depending on how you want to call it. And so what we're going to do is, I have this old weird plotting program that I use, but we can just go through the steps. And you can do this in Excel really easily, and we can do it in MATLAB really easily. I don't really know the MATLAB syntax, so I trust that if you know MATLAB, you'll easily be able to translate what I'm saying into MATLAB. And if you know Excel, you should be able to do it pretty easily just by putting numbers into cells and then filling a couple columns with numbers and then plotting it. All right. So how many of you guys are going to use MATLAB? And how many are you going to use Excel? Okay, it's a tie. So we can have a race. So just out of reference, the last time I did this at the CIDR in 2011, and maybe how many of you guys were there and did that? And so what was funny, and I found this kind of funny, the first thing we're going to do is plot power law on a log-log plot, just a single line that's a power law. And it took like 30 minutes to accomplish this. So we can see if you guys are on the ball, and we can maybe do that in 15 minutes this time. So what we're going to first do is go back and looking at, let's see here, is there a pointer still? I don't see one. But looking at this relationship here, there's this line, the piezometer line. Piezometer is stress meter, and watt meter is stress times strain rate or dissipation rate meter. And they're basically the same line to a factor of 2 or so. So what we're just going to do is plot this line on a plot of stress versus grain size. And I want to remind you where it came from. It looks like I didn't put it there. Oh, here we go. Yes, remember this figure from yesterday? So there's this relationship between stress and grain size. And before we plot it, if you guys want to get started plotting while you're listening, all we're going to do is plot. Where'd it go? Dun, dun. Keep on losing figures. There. We're just going to plot this line right here. But while we do that, I just wanted to motivate what that relationship is. So if you have a grain boundary, and imagine there's two crystals that have slightly different orientations, and they're being deformed, and as a result, they're deforming at different rates, and they have different dislocation densities. Can you imagine that? And so I'm just going to put these upside-down T's in here, and I'm going to put more of them there than here. Okay, so remember from our cartoon of a dislocation that we're kind of ripping apart the bonds here and smashing them together here. So we're elastically deforming the crystal. And as a result, we're like making the bonds want to be a certain length, but we're putting a stress on them by forcing this deformation, elastic deformation around the dislocation. And we can quantify how much energy that is. And so it will be cast in terms of a strain energy per unit length, or energy per length of the dislocation. And so that energy per length is proportional to the shear modulus, elastic modulus, and the Berger's vector squared. And so if we want to get energy per volume, we just take mu b squared times the dislocation density, which is length per volume. And when you do that, then you get energy per volume. So joules per meter cubed. So the higher the dislocation density, the higher the strain energy per unit volume. So it's getting more and more unhappy. So this grain boundary can kind of sense that. And what will happen is it will bulge out like this. And so you create new surface area, but you're replacing that area with a bunch of dislocations with a new strain-free area. And when you do that, you create a bulge with a radius of curvature that we can call r. And there's something called surface energy. So that's joules per meter squared. That's any grain boundary will have some energy associated with because the bonds don't match very well. And if we take that surface energy and divide it by the radius of curvature, we also get joules per meter cubed, so surface energy density. And so you can have this grain boundary bulge with the radius that gets smaller and smaller, the larger and larger this dislocation density gets. And it's a steady state process. So at steady state, these things can kind of be approximate to each other. And so R is kind of like grain size. So you can see that the grain size will be inversely proportional to the dislocation density. And the dislocation density depends on stress. And you turn all of that into a relationship then that gives you grain size is proportional to stress to the minus 1.3 power, roughly. Now, in these plots, we're going to turn it into stress grain size. So we just have to solve that equation with a proportionality constant. And that's what this is up here. So this is that equation. And that equation is for grain size in millimeters and stress in megapascals. All right? So is that clear? So how many of you guys have already plotted it up? Awesome. All right. Now, so I'll plot it up too. But before I do that, yep.
Do we expect to download any files, any data from?
Nope. It's just going to be on your computer forever. There's not going to be any downloading. Before we do that, yesterday I was trying to run a couple movies that, of course, didn't work. And I figured out why, and I fixed them. But I thought it would be worthwhile to show you guys a movie. This is a nickel aluminum alloy, but this is a movie taken in an electron microscope where they were deforming the crystal. And so these are the little dislocations marching along. The scale, this is like a micron, is like this. So those things are roughly a micron apart. And then here you can see the nucleation of dislocations, these weird whips. So they start growing, and then when in that picture I was showing yesterday, when they actually touch, then they'll go boop, and they'll disappear really quickly. You see how it's like really herky-jerky? So the dislocation loop is growing, and then it gets to a point where it's free to move, and then it just takes off. And so at the beginning of the movie, you saw the other thing that the dislocations wanted to.
So, Greg, sorry, those things we're seeing moving, those are the dislocations?
These are the dislocations. And I'll explain what you're seeing here in a second. So dislocations, like you can see in that cartoon up there, you're warping the lattice. And so if you have an electron beam going through a really thin part of a crystal, you get diffraction conditions that are different around the dislocation line. And so the black lines are they're that effect that you're seeing. I'll put this movie, I'll figure out how to get that onto the thing. But so these are, and so you can actually see, in a sense, the strain around the dislocation core, which is this high energy source, which is driving the crystallization. These are the dislocations, these lines. Yeah. Yeah. We can look at one other movie. It's probably worthwhile to do that. It's a little bit slower. So in this movie, you can see how they march along, and then one gets stuck on that thing that crosses the screen. And they all are stuck, and then they get past it, and they go doo-doo-doo-doo-doo, and they run up. So that's like the glide is really fast, and then it gets stuck, and it waits around until the condition allows it to move again, and then they all march again. And you can see the way the elasticity is working is they all stay perfectly the same distance apart from each other. And that's because the stresses on the dislocation depend on how close they are, and they're finding that equilibrium that depends on how high the stress is. Yeah. So it's like it's a little fancy stage that you have in the TEM, and then they can pull on it, and so they can see the deformation occur. That's pretty cool. Yeah, so you see how those are called slip lines, and so what you're seeing is those loops are all going down through the crystal, and those lines are forming from where the dislocation's moving along. So different diffraction stuff, and those other lines are dislocations that are stuck, and that's kind of what the obstacles are. All right, so I'll put those on the wiki. No, this is nickel aluminum alloy. Very important geologic material at very reducing conditions near the core mantle boundary. So I don't know. That was real time, yeah. Okay, so back to the deformation mechanism map. So so in my silly program, I can. Let's see here. Whoa. I can just create y equals 7.6 times x raised to the minus 0.75 power. And then here I'll do it from, this is looking at grain size, and so I'll do it from like, in millimeters, maybe I'll do it from 0.01 to 10. All right, so you can do that really quickly in MATLAB, and in Excel, right? You can just say, equals this, and then put some number in one cell, and then have like 1, and then 2, and then drag it down, and then that's how it works in Excel, right? Anyone in Excel have it already plotted? That was easy? Yeah, all right. And so then we want to make it a log-log plot. Oh, what the hell happened? So I'm just going to, in this language, just make it a log-log plot. And plot it. See what I get. And it doesn't show up, of course, because I had axes already set. All right. So you guys should get some line that looks like that. Okay, so this is like and so this is log of stress. So this is 10 MPa, and at 10 MPa, the grain size is a little less than a millimeter. Right? Are you guys getting that? Awesome. All right, so we did that in much less than a half an hour. Is anyone still fiddling? No? You already got it? Okay. So the next part on here is we want to put strain rate contours on this plot. Okay? And so this is where you use flow laws. And to do that, you're just going to have to set up some variables. And we'll use these variables. And so what's going to happen here? So these are a set of flow law parameters for olivine. And I'll remind you of the flow law form. So we have the strain rate is equal to A times stress to the n power divided by grain size to the m power. I don't even have it in there. Oh, it's p power, of course. P power. And then we're going to do this for a constant concentration of OH. So the COH to the R power. And then we have an exponential term. Where this is the activation energy, and this is the activation volume. So this whole thing is the activation enthalpy. So that's the temperature and pressure dependence of the deformation. It's exponential, so it has a huge effect. And this is temperature and the gas constant. So temperature, always remember, whenever you use these type of thermodynamic equations, you always use temperature in Kelvin. So one of the first things that always happens when people do homework problems and they come and they tell me that they can't get the right answer, you do this enough times, you learn to say, did you use temperature in Kelvin? And they go, oh, no, sorry. And then you go back. And the other thing that's super, super important, and there has been hideous mistakes in the literature by making this mistake, is you have to make sure that your units are all consistent. Okay? So you need to make sure that your units of this pre-exponential constant match the units of your water concentration, grain size, and stress. Okay? So there's a really good trick that you should try whenever you're using these equations. And this little Excel file or MATLAB code that you're writing, you can use this to check it. So if you want to run a program on convection or looking at Rayleigh-Taylor instabilities or looking at the strength of a fault, and you want to use a laboratory flow law, you should always check that you reproduce the experimental condition at the stress and temperature of the experiment. And if you don't, then you probably messed up. 1 out of 10 times, it will be because the person who wrote the paper has a typo. And then you can email them, and they'll go, oh, yeah, that typo's been in there for 10 years, and I should have written a correction but never did. So there's one other thing that people do that's cheating, and it's like something that's important. There'll be uncertainties given for these parameters. And so a lot of people rightly will, in their codes, they'll see what the effect of changing the activation energy or the stress exponent is within the uncertainty of that value. However, when they do that, you have to be absolutely careful that you remember that the uncertainty in these parameters, so that the ones that have uncertainty are E, V, R, N, and P. All those have uncertainty in them. The uncertainty of all those parameters co-varies with the uncertainty of this. So if you just change the activation enthalpy or energy without changing this, what will happen, I'll just draw a plot of what the effect of that is. So if you look at log of strain rate versus 1 over temperature, you get a negative slope. So this is an Arrhenius relationship, right? And so maybe there's some data in there that you fit. And you get the slope of that is minus E over R. So if you have some uncertainty with that, the uncertainty would look like this, right? If you don't change A, when you change E, what you'll get instead is this. And that will be like 5 orders of magnitude because it's an exponential term. And so it turns, I'll tell you a little story. I'm not going to blame the person, but there's a very famous and influential earth scientist that told people that the laboratory flow laws aren't really useful because the uncertainty in the activation energy made them almost worthless. And he was very influential, and it really have influenced a lot of people's opinions. But what he was doing was this calculation and not correctly accounting for the covariation in the activation energy. Maybe one day if I have a couple beers and you ask me who it is, I'll tell you who it was. But I'll protect them from the time being. I have a paper where I have a paper that it's in reviews. It's reviews in mineralogy, I guess, paper from 2002 that has that warning in it. It's not one of my best sellers, so. Yes. Yeah. Yeah, this was. Yeah, it's like, oh, that's cool. It makes it more interesting. Yeah. But so one other thing, and this is also a true story, and I'll protect the names to protect the guilty. There was a review paper, a very prominent review paper that tabulated all of these parameters, and they gave the A in gigapascals instead of megapascals. And so you take this number, which is 3 orders of magnitude to an exponent of 3. So it gives you answers, and maybe part of the origin of what Torsten was talking about, answers that are 9 orders of magnitude wrong. And so people were like, wow, convection's not happening. This flow law is clearly wrong. Okay, so what we're going to do is you're going to set up, we'll do dislocation creep first. So we'll plot up wet dislocation creep with constant COH. And before we talk about that, I thought it would be worthwhile just to show you kind of where these types of things come from. So you guys have all heard of the effect of water on rheology. And when experimentalists do this, if you want to control the water content, you try to do an experiment at constant water fugacity. But if you're a modeler, you don't really want to have to figure out what water fugacity is in your model. It'd be a pain in the neck. It's like what Raj was saying. He hates oxygen fugacity. Well, I hate water fugacity. But I don't mind water content, because what you're really seeing is that the rheology is changing. This is at a constant temperature, stress, and normalized pressure, how the strain rate varies as a function of the water content in the crystals. So the water contents are measured using infrared spectroscopy. And with all those parameters, you can see from these 6 different studies, so 6 different labs, how you get a trend that has a lot of scatter in it, but you can clearly see how by the time you get out to values that are consistent with what you have in the asthenosphere, that the effective viscosity is decreasing by like a factor of 30 to 50 or something. And so that's a big effect. So instead of having to deal with water fugacity, it's much easier just to deal with water content. And so these flow laws here have a term in them here where you just take the water content, and the slope of that power law was 1.2. And so this number, this 90, has the units that would be correct for having water content in hydrogens per 10 to the 6 silicons. Okay? So what we want to do is we're in the deformation mechanism map. We're going to plug in these parameters. But we have to do one more thing, because the deformation mechanism map is plotted with contours of strain rate. So we have to solve this equation for stress. Okay? So you just take So that's the equation that we're going to draw. And this will take longer to do, but it's not that hard. So the stress is just equal to the strain rate with all this other junk in the denominator taken to the 1 over n power. All right? Yeah, that's what I'm going to walk through it now. So we're going to use these parameters. So A, we're going to set a variable A equal 90, N equal 3.50000. No grain size dependence. This R value of 1.2. Activation energy of 480. That's in kilojoules. A is in joules, so we'll have to make sure we do that correctly. And then an activation volume of 11 meters cubed times 10 to the 6 meters cubed per mole. Okay, so if I see here, I'll send you guys this paper, but it'll be on the screen so you can see it for writing this stuff up on there. Can you see that? Is that big enough? Okay, so we're going to do. So another thing that's handy about having something like this is that you can stick in these in these things, and when you stick in the numbers, that you make sure you get the right answer out before you spend a bazillion years having it run in a convection code or something. I don't want to do it there. That'd be stupid. All right, so I'm going to start. This is just writing a little program that you do the same thing in MATLAB, or you'll make just define a cell in Excel. So I'm going to set a variable A equal 90. Set a variable N equal 3.5. Set a variable R equal 1.2. Set a variable E equal, and this is another thing that you have to make sure you do. You have to make the units of your activation parameters the same as your units of R. And so R is typically given in joules. So the activation energy was 480 kilojoules per mole, so that's 480,000 joules per mole. How many of you guys have any inclination of what the activation energy is and what that means? None of you? Other than it's a... What's that? Yeah. So right. So for this case, what it is it's probably the rate limiting step in that diffusion process where the dislocation moved. And so it's related to the energy it takes to make the defect and the energy it takes to make the defect move. So it's that combination of two things, and it has that exponential dependence to it. Okay. And we'll set a variable R. Yep, did someone have a question? And let's see. So activation volume is 11 times 10 to the minus 6. Okay. All right, so what temperature should we do? What temperature do you want to do the deformation mechanism map? Maybe 1200 degrees C? Yes? No? Sure? Let's do 1200 degrees C. So the deformation mechanism map is for constant temperature. So the way I do that, just so I don't have to do a bunch of math in my head, is I do 1200 plus 273. So that way I can always, instead of having to go 1473, what is that in units that I like? And what I really should do is just be much more handy with Kelvin, but it's the same way. Like I don't know what room temperature is in Celsius unless I'm in Europe for a week. Okay. And how about what pressure do you want to do? Let's do the base of the lithosphere or something. And okay, so this is another one. So we have this term in joules. So we want PV in joules. So what's the unit that will give me joules in PV? What units of pressure? Pascals, exactly. So what's the pressure at 100 kilometers in pascals? So how many gigapascals? Let's start with that. 3. Yeah, let's just do 3 gigapascals. So we'll do 3 times 10 to the 9. Okay. So then we need a strain rate. So base of the lithosphere, let's just do 10 to the minus 15 for starters per second. Okay, so now this is another thing. What the hell does strain rate, sorry, Slider, what the heck does strain rate mean? So one thing, there's kind of some bounds. You can kind of think, well, a plate is moving at 3 centimeters per year, which has a very convenient unit of 1 nanometer per second. And maybe convection's occurring over 1,000 kilometers. So that's 10 to the 6. So if I have a strain rate, which is 1 nanometer per second over 1,000 kilometers, that's equal to 10 to the minus 9 divided by 10 to the 6 meters. So that gives me 10 to the minus 15 per second. So that's kind of where, as a ballpark, that number comes from. It's like plate velocity over thickness of a convection cell, roughly. To give you another good number that you can kind of keep in your back pocket, 1% strain in the age of the Earth is essentially not deforming, and that's around 10 to the minus 18 per second. So if you do something and your strain rate's less than 10 to the minus 18, then that's basically not deforming. And then another example of like, well, what's the fastest strain rate you can envision? But strain rates in shear zones, maybe the fastest ones may be something like 10 to the minus 9 per second. That's really hauling. And then in an earthquake, it's enormous, right? So it's maybe a meter per meter per second over a millimeter. So then that's like 10 to the 3. So the range of strain rate in the Earth is something in the range of 21 orders of magnitude or so. And that's why, guys who are running computer codes, you don't do convection in earthquakes usually in the same calculation. But maybe now you can. I don't know. Yeah, there's elasticity. That's right. That's a great question. But if the deformation in the lower crust in the San Andreas Fault is occurring about a kilometer, then it's 10 to the minus 12. So that's kind of a good lower crustal shear zone strain rate if the shear zone's a kilometer wide. Okay. So now we're going to plot that thing. We need to set the other variable. So now I can just create this thing again. And so I have the rate divided by, and I'm just going to put it in parentheses to make sure I don't mess up. No, we didn't set the water content. Let's set the water content equal to 500. So that would be not an that's something like 50 ppm or something like that by weight. I screwed up. Sorry. Don't copy me. Get rid of this. That's what we're solving for. All right. So we have rate divided by all this other junk, A, COH, and then the exponential term. And then I have to close the exponential and then close the whole thing. And there it is. Okay, and so, and we'll do this from 0.1 MPa to 100 MPa. Right. Oh, shit. What am I doing here? That's not right. I don't have to do that. This is grain size. Sorry. I'll be back with you in just a second. All right. So let me go back to the plot here just to remind myself what we were doing. Okay. So what we're going to do is make one of these dislocation creep contours. These are in microstrains per year, so we're going to get different units, but we're going to make a line on this type of plot, and so we're going to do it from a grain size of 0.1 millimeters to 100 millimeters. So this is kind of a funny thing to do because we're making a line where there's no x variable. So it's just a constant that I'm going to draw along a line. And I don't know if you can you guys do that in Excel? That's a good question. Can you make a line with no slope in Excel? What's that? Yeah, you just make that value constant. Yeah, that's right. Okay. And then we're going to let that be the log of the value. And then we'll see if it works. Oh, come on. So DMM is deformation mechanism map. Come on, stop doing that. Okay. So I could have had that all written already, but I thought, for crying out loud, where is it? But I thought if I wrote it at the same time you did, then we would be done at about the same time. All right. So let's see if we got the right answer. It doesn't look like the right. Oh, that's right. I didn't. It should be something like 1 MPa. So we didn't get the right answer. So this is a good example of how we should be able to figure out why. So did any of you guys get something like 1 MPa? Did you guys have any of you plotted it yet? Looks right. What the hell's going on here? For crying out loud. What the heck's going on here? Well, let me try something slightly different. Okay, this is a good way of checking. So let me just really quickly do something.
Correct. What would be unit for the stress here?
It should be megapascals. Yeah. All right. Let me do another.
Something like 1.26.
You got 0.26? Yeah. So you got the right answer.
How do you know?
Because I know that that's about what the right answer should be, just from knowing the conditions of the deformation. What the hell? Sorry about that. Yeah, that should be okay. All right, I'm just going to do something really quickly. So if I just say evaluate. So this is a kind of A times 100 raised to the n times COH raised to the r times exponential of minus E plus PV divided by R divided by T.
You missed the parentheses.
What's that?
And correct, I think you missed the parentheses somewhere.
Yeah, that's what I'm guessing.
I'm writing
At
the code
the
in C.
beginning, maybe you should put the bracket at the beginning.
Put the parentheses.
Yeah, now it says that I have too many. Okay. This is great.
You miss one at the beginning before the rate.
So I have this one, and then I have the denominator. So 1, 2, 3, 1, 2, 3. That looks right, isn't it? 1, 2, 3, 4. 1, 2, 3, 4. I need another one. You're right. But it says oh, for crying out loud. Yeah, there's something. What's that? Yeah, that's it. I got it. So that's Jesus Christ. What is going on here? What is happening? Yeah, I was just plotting it over a line. Evaluate. 100.
At the end of the experiment, it's still doing FE plus B by V over R over T.
Exponential of minus E plus. Right. I need.
Supposed to be R over T or R?
That's R T there. If you like, I can do it like this. It's like the program freaked out. That's really strange. Well, so this is just the exponential of minus e plus p times v divided by RT. So that's right.
I just want to understand the syntax. What does that mean? Create and slash create dash f and dash t. That means because you didn't put the green size in this.
Yeah, this is just calculating a line that's constant in stress.
But I mean that probably the problem. The result should be a scalar, but
It should be a scalar. You're right. So, and I'm just plotting a line that is equal to that scalar along the x-axis, but it wasn't giving the right number.
I mean, why don't you put the green size in that expression?
Yeah, if you wanted to, you just put.
Set p equals to 0.
Let me just try. This is ridiculous. God. All right. I am. So, what are you guys getting for that answer? Has anyone just figured, if you just plot, this thing seems to be freaking out. As an example, put in 150 there, put in, what do we have here in this thing? So see here, right here, we should be able to do that one right there. So 90 times 0.3, that's 0.3 MPa, 1,000 to the 1.2 power, and then this in exponential term. I have no idea what's going on with this thing. Right, so if you do 90 times 0.3 raised to 3.5 times 1,000 raised to 1.2 times exponential of minus 480,000 plus 1e9 times 11e minus 6 divided by 8.314 times 1673. It gets the right answer, of course. So what the hell's going on with this other macro? This is insane. A times. I'm really, really sorry, guys.
Greg, can I ask you a question about the equation itself?
What's that?
We've been kind of talking about this here, but so the exponent on D is the P. How is that determined? Is it an experimental number? Or does it depend on y or some 0 to some degree?
Right. Okay. So at least we can do that. I don't understand what the heck's going on with that. The macro that I was running. Okay. So in the dislocation creep field, there's no grain size dependence. So d to the 0 is just 1. So in the diffusion creep field, the strain rate is proportional to 1 over d to some exponent p. And so the way you would do it was you would have a constant temperature and stress and do a bunch of experiments where you measure the strain rate versus grain size. And you would do that by making rocks that had different grain sizes and doing an experiment. And you would plot up the data and then just fit it, and that slope will be equal to p.
So is that the difference between like grain boundary and
Yes. So remember yesterday I talked about the diffusion gradient. So that one of the grain size dependencies from that. The other is from you're taking a displacement rate and turning it into a strain rate. So that's the displacement rate divided by the grain size. And then the last one is related to the grain boundary diffusion. So if it's grain boundary diffusion, you have a grain boundary width divided by grain size term. So you end up with d cubed.
So then these are technically experimentally determined.
Yes, these are all experimentally determined by that. All right, so now I have absolutely no idea why this is not working, other than that I have some retarded. Oh, I see. This is retarded. This is a great example of a syntax problem. Got it. Sorry. I have 2 R's. It's not case sensitive. Jesus Christ, man. I'm sure some of you have been there before in your life. Yeah, this is great. Are we allowed to delete this? So I was. What's that? Thank you, Emily. That's unbelievable. And you can see in this game of power laws where a little mistake can lead to big problems. All right. And so, Gigi, you were able to do it because your program was case sensitive.
Yeah, I use C.
Yeah. Okay.
Along those lines, there's this other software called GNU-plot,
Yeah.
GenPlot, and that allows you to basically do the same thing, but it looks a little bit simpler than what you're doing right there. And
Yeah.
it's case sensitive.
But new plot would require me to learn it.
It's basically like what you're doing right now, leaving away the set plot.
Yeah, all right.
It won't allow you to make mistakes.
It won't allow me to make mistakes. But it would have, in this case, it would have allowed me to have had two different cases and it wouldn't have been a problem. All right, so that was genius. So now, after that, how long did that take? 25 minutes to do that? All right, now we're going to do the same thing for a diffusion creep line. Okay? Are you ready for that? How long is that going to take? That's another line. So this reminds me of I was making fun of the people at the last citer for not being able to draw lines. So, okay. So now we need to. What's that? That's a log plot. Yeah. Yeah. All right. So if my student did this, I'd get mad at them for giving me a plot that didn't have axis labels on it, and we'll fix that in a second. So now we want to add in the diffusion creep line. And so we'll use, again, the wet diffusion creep law. So that's listed there. And so we have to go through the same exercise again. And so we have to set a bunch of new variables. So wet diffusion creep is 1 times 10 to the 6. No, how about this? I'll put a W there just for the hell of it. Ah, shit. It's linear, so the stress exponent is 1. The grain size exponent is 3, but we're going to call it PW so it doesn't get mixed up with pressure this time. The water content exponent is just going to be 1. Activation enthalpy is 375. And that's 4. Okay, and so then I can just copy this thing, dump it down here, fix all of these. And I have to add in the grain size effect. And grain size is the variable, so this time you guys can be happy that there is a variable there. Okay. What's that? Yeah. Ah, awesome. Thank you. All right, and we'll let diffusion creep be red, and then we'll overlay it. Okay. So we look at this plot. Aha. Now this is another good lesson. This was in microns, so I have to go in here. And so my plot is the plot is this is the how should I do this quickly? The flow law is in microns, and so I'm making the plot in millimeters, so that's a little bit confusing. So I had to change that to microns up here, and then I'm going to take to turn it into millimeters, I can just come in here and divide that by 1,000. So I multiply it by 1,000 and divide it by 1,000, because just to make it clear, this A thing is in microns, but I'm plotting it in millimeters. That's not right. What the hell? That is unbelievable. That's because, God. Right. No, that's okay. All right. Let's see what I got to do. All right. So, how are you? Are you guys faster than me? Do you get to have a plot now? So, this is now showing a strain rate increasing on a power law of 3 for diffusion creep. So, the crossover stress is this is 0.1 MPa, so this is something like 0.3 MPa. And the grain size is something like 300 microns. Okay? So I can make it, so that would be at a strain rate of 10 to the minus 15, right? Have any of you, I mean, now that I screwed this up, are any of you guys getting a plot that looks like this? No? Yeah, okay. So this first line, this is the strain rate of 10 to the minus 15, and this is, we solve for stress, right? So if you go back to, if you go back here, so in your program or whatever you're doing, we solved for stress in the flow law, and I didn't put x as a variable because the thing doesn't depend on x, so I could have put it in to the 0 power. So that was the line. And then we solved for the stress for diffusion creep down here. Yeah?
I still can't understand why in your experiment you have R over T, because on the equation you wrote before it was R times T.
Yeah, so in the syntax, this is, in this syntax, R is, you're dividing by R, and then it does the whole thing next, and it takes all of that and divides it by T. So it's the same as putting the T in the parentheses. Yeah. You can write it. If you did, even in Excel, it knows that, I think. If you can do it either way. You can put the R times T in parentheses, or R and then divide it by T.
Yeah, my experiment just didn't work. So that's
All right. Yeah. Okay. So the plot was in millimeters. So let's go back here. All right. So this table, so A has units for stress in MPa and grain size in microns. Okay? So in order to make the deformation mechanism map that had grain size in millimeters, when I plot it, I have x, which needs to be in microns. And so I just took 0.1 millimeters, multiplied it by 10 to the 3 to turn it into microns. So there's 1,000 microns in a millimeter. Okay? And then since I wanted to plot it in millimeters, I took that value of x and divided by 1,000 when I plotted it. Yep.
The stress exponent, how do the units of the strain remain consistent?
So
So if you change the n from 1 to 4.5.
So the A value for the diffusion creep has different units. And so the easiest thing to make sure that you just do is so the A value will have units of MPa to the minus n, right? And so, but as long as you remember to keep the units consistent, then you'll be okay. Okay, so did you? How many of you guys have a plot that looks something? All right, Nick and Gigi. All right. Any other questions about it right now? I can wait a little bit longer before we do the next step. Yeah.
This figure is smaller, it's still not large, but it looks like linear, right?
In which this figure?
Yeah.
Yeah, here. Let me, if you like. Does that look better? Yeah. And then, while some of you are, we can. Oh, that didn't work. What the hell? Why didn't it work? That wasn't. What the hell's going on here? This is unbelievable. Okay. So some of you have this now? How many of you guys have it now? A handful. We can, well, I'm going to change it a little bit. it won't take you that long to catch up, but we'll try to get a couple more things plotted on here, then we can call it good. So what should happen to the diffusion creep flow law if we change the strain rate by an order of magnitude? Well, how much will the stress go up? How much will the stress go up if I change the strain rate by an order of magnitude in the diffusion creep field? An order of magnitude, exactly. How much will the stress go up if we change the strain rate in order of magnitude in the dislocation creep field? A little bit, maybe a factor of 2. Okay, so let's try that. And it won't, if you guys don't have it yet, it will be relatively fast to fix once you get it. In which one? Here? Yeah. Right here? Yeah. Thank you. That's going to make a difference. All right, so all right. So it looks kind of funny, but so we increase the strain rate by an order of magnitude in the dislocation creep field, and the stress increases by roughly a factor of 2. And we increased in the diffusion creep field, and it increased by an order of magnitude. So I'll change the scale so you can see that easier. And then we'll see if you guys have how we're doing with time and whatnot. Okay. All right, so this is now starting to look like the map in the figure here. So we have lines that are going up with the slope of 3, and then these constant lines. And so I want to just do a couple more things, and then you'll have a deformation mechanism map, and then we can talk about quickly some stuff that you can use it for. So what we can do now is plot on here that we can plot the recrystallization line on this thing. Remember that the very first thing we did? So that we can take this relationship, and it will plot something like that. And the other thing that you can see on here so what we have this line and this line, and we have to kind of figure out where would we be. So all we've done is like drawn some strain rates. So we can think with this map, we can now think of how to use it. Okay? And so to do that, we need to remember that the strain rate of these two mechanisms are independent of each other, right? So what does that mean? That means that they're running at the same time. The dislocations are moving through the crystal, and the diffusion creep process is happening at the same time. Okay? So what that means is that the strain rate, that's the total strain rate, is equal to the strain rate of diffusion creep plus the strain rate of dislocation creep. And so the way that will look like on this plot, so we have log of strain rate versus the log of grain size. And here's the dislocation creep line. And here's the diffusion creep line. Oh, shit. This is stress on our plot. Sorry. So what that means, instead of strain rates, by having it as stress, it's the weaker mechanism wins. So you would follow this line, because it's easier to deform by diffusion creep. Then you'd switch, and you'd follow that line. Okay? If we did it as a log strain rate versus log stress plot as an example, you would have this n equals 1 line and this n equals 3 line. And you would go along here, then you would switch and go up that way. Okay? So a little bit of a tricky thing is it doesn't actually go exactly to this margin and move over to the other side. It would actually curve over like that. But we're not going to deal with that right now. That's just, if you didn't account for that, your viscosity would be wrong by a factor of 2. So a line that goes off like this would be the boundary between the two mechanisms. Okay? And if you can solve for that, if I didn't take 25 minutes to figure out that I had those double R's in there, what we would have done is we would have solved for the stress grain size boundary between dislocation creep and diffusion creep and plotted it on the diagram. Okay? So what's that mean? That's the strain rate. It's the stress and the grain size where the strain rate of dislocation creep and diffusion creep are the same. So that's the mechanism boundary. And if you like, you can think of that as the anisotropy boundary between diffusion creep and dislocation creep if you're a seismologist looking about shear wave splitting. All right, and so how would you do that? So it's not that hard to do. And you can do this as a homework assignment, if you like. So you have A stress to the 3.5 times the exponential term, and you're going to set that equal to AW that we call the diffusion creep thing, times stress divided by D cubed. And so you'll have if you solve that equation for stress, you can plot it on that curve there, right? So you get stress to the 2.5 equals AW over A times the exponential term for the diffusion creep divided by the exponential term for the dislocation creep. And I'll just do that for the sake of time. Times 1 over D cubed. And so then stress is going to be proportional. What's that? So stress will be proportional to 1 over D to the 3 over 2.5. So a line, that line would run like this. And so if you go back to this plot here, that's what this black line is here. And so this is the deformation, the mechanism boundary. And then the other thing that we can do is plot this line on here. So what you can then do with this is figure out, if you like, you can turn these plots into viscosity versus grain size plots just by dividing by stress and strain rate and making different plots. But the key thing for this plot is it's for a constant temperature. All right. So if you can make these plots in all different ways. So you could do it for a constant strain rate, but different temperatures is another common plot to use. And the reason it's useful, if you're running convection codes, you can kind of make sure that the mechanisms that you can see which mechanisms are dominating where in your codes. But you can also do things to compare if you're a geologist to look at your rocks. So how do they plot on a thing like this? And so one of the main things that people are worried about right now in trying to understand the rheology is because the diffusion creep field has this really, really strong grain size dependence. We need to understand where the grain size is in the mantle, and that piezometer relationship over here, for this high temperature, it plots well into the dislocation creep field. But one of the things that you can do with this type of diagram is if you change the temperature to a much lower temperature, you'll find that diffusion creep thing moves into the recrystallization line moves into the diffusion creep field. And so that was what you can do with as I'll send you an email of a bunch of stuff to try to make sure that your codes work, and you guys can bug me later and tell me whether it's working or not. And then I can also just send you the code for making a strength depth diagram, and you can try that out. So that it just requires a little bit different manipulation of the data sets.
Can I ask, you mentioned, I'm just trying to catch up, when you mentioned there was a problem with units with microns and which units,
Yeah.
was that?
Okay, so if we go back here, let's see. So this is kind of the thing you want to make sure you're checking on. So the flow law has this, so that you can see the A is just really it has a theoretical basis, but it's a fitting parameter essentially. And so when the flow law was created, in the diffusion creep field, the grain size was measured in microns. Okay, does that make sense? So when I started making the plot, I was trying to copy that other one, and the grain size was in millimeters on the x-axis. So instead of changing the value of A, which given the way things were going might have taken a half an hour, I instead, in the code, this thing is in microns, and I wanted to, but the plot x-axis is in millimeters. So this was the range of the x values that I was using. So it's 0.1 millimeters, which is 100 microns. So I just switched these to microns. But then my x values are in microns, and so I wanted to plot it in millimeters. So here I just divided it back by 1,000 to get it back where it was. All right, so time is up. I'm really sorry about my syntax goof up, but I'll make sure that you guys have examples of these programs. I don't know how to. I'll just make sure Cinti gets them, and then if you're interested. So I'll send you one for the deformation mechanism map, and then I'll send you. Why the hell is this working? I'll send you this one. And so this is a strength depth diagram. So this is just showing you now how the stress on a flow law varies as a function of depth, which is, in this case, it's temperature. and how the stress varies as a function of strain rate. And then these lines are the brittle deformation lines, the frictional lines. And so the things that you need to have in there are a temperature gradient, a pressure gradient, a law for friction, and a law for the flow law. And so I'll give you one of those things to use. And so the way you can think of the deformation mechanism map is it's kind of like a cross-section through here with grain size as another variable. It's only at a certain depth. All right, so we have to break now, right, Cincy? Is it? Yeah, enough torture. Okay. Well, anyway, I think at least you guys could see some of the foibles that you get when you're using these flow laws. And if you please bug me if you want to learn more about this, or you can bug Janelle. She's at World. I don't know if Janelle's here. She probably said she didn't have to listen to this. Janelle is a really good expert at deformation mechanism maps. And then, and I guess I want to stress again why you would ever use these things. So they're very useful for trying to interpret where your rheology is in terms of a mechanism, and that's not trivial because it's important for understanding where you might expect strain localization and where you might expect seismic-anisotropy to begin. Because the grain size sensitivity of the diffusion creep is really critical for understanding strain localization, and the stress dependence of dislocation creep is important for giving you low viscosity regions where you have rapid strain rates and things like that. And so it's a good intuition building thing. And then the other part about it that's really helpful, as you know, so in this case, I was running the program and it was working fine. It was just giving me numbers that I knew were wrong. So the other real important lesson is make sure that you check your law against the data that it was obtained with. And then the last one is don't just change the activation energy or the stress exponent without changing the pre-exponential term. Those are the other lessons. But I'll be happy to talk to you guys at coffee break later on about this. And sorry again for the mess up.